Hello. In this video tutorial, we're going to take a look at the solutions to wave functions practice. Please remember to pause or rewind the video as needed. Let's begin. A simple harmonic motion oscillator executes its motion as x is a function of time is equal to 0.20 meters times the cosine of pi over 2t. For all questions below, make sure to include the correct units. Okay, let's first begin by acknowledging the fact that we are looking at a cosine function. So we're going to be going between the position as a function of time would be a, the amplitude, times the cosine of omega t. The corresponding velocity time function would be, if you remember the pattern from last week, it would be going from cosine to sine, or negative sine rather. So negative a omega sine omega t. Okay, where this is x max, this is v max, and then finally the acceleration function, which is going from negative sine to negative cosine. So negative a omega squared cosine omega t, where a omega squared would be a max. Omega, as you can see, is a part of each of the functions, and it's the constant right in front of t. So let's take a look at our function. From this, we can tell what our amplitude is, and we can tell what our omega is. So what's the amplitude? The amplitude is going to be 0.20 meters. Get that right from the function. The period of oscillation, we can use 2 pi over omega. Remember, omega is pi over 2 radians. So 2 over pi divided by pi over 2. Well, 2 pi over 1 times 2 over pi. Remember, when you're dividing fractions, you invert and multiply. The 2 cancels, and what does that tell you? The oscillator is going to repeat every 4 seconds. Part C, the frequency of oscillation. Well, frequency is just the inverse of the period. So 1 over 4 seconds means it's going to repeat every 0.25 cycles per second, or 0.25 hertz. What is the maximum velocity of the oscillator? Well, that would be a omega. So V max is going to be a omega. So it's 0.20 meters times omega, which is pi over 2 radians per second. Throw that in your calculator, and you're going to go pi divided by 2, which is roughly about 1.57, times 0.2, and we get about 0.31 meters per second. What's the velocity at 2.5 seconds? Well, we need the velocity function. So if the velocity function is negative a omega sine omega t, what that would be is negative 0.31. So negative a omega is 0.31 sine of pi over 2 times t, but t is going to be 2.5 seconds. So we're going to put in times 2.5 seconds. So V at 2.5 seconds is approximately, you're going to start by multiplying here. So pi divided by 2 times 2.5 is 3.92, right? You want to make sure that your calculator is in radians mode, because you're going to be taking the sine in radians. So we're taking, pi divided by 2 times 2.5 is 3.92, and we're going to take the sine of that. And then we get negative 0.707, and we're going to multiply that times negative 0.31. Okay, and at 2.5 seconds, the velocity is about 0.219 or 0.22 meters per second. So it's going about that fast at 2.5 seconds. Okay, what is the maximum acceleration of the oscillator? Well, A max you can find by going A omega squared. So that one would be 0.2 meters times pi over 2 squared. So what we're going to do is we're going to go pi divided by 2. We're going to square that, and then we're going to multiply that times 0.2. And so we get roughly about 0.49 meters per second squared. If the oscillator is a 10 kilogram mass oscillating on a spring, find the force constant. Okay, so here's what we know. Omega squared, this is for a mass spring system, okay? So T equals 2 pi times the square root of m over k, which is the same thing as 2 pi over the square root of k over m. Now remember, T is also 2 pi over omega, so that means omega is the square root of k over m. Or we could say omega squared is equal to k over m. So solving for k, the force constant, the spring constant, k would be equal to mass times omega squared. 10 kilogram mass times pi over 2 squared. So let's go pi divided by 2, hit your x squared button, times 10. And we get roughly about 24.6 or 24.7, I'll just round it up, 25 newtons per meter. Okay, what is the displacement of the oscillator at t equals 2.5 seconds? So x as a function of time, again, is 0.20 times the cosine of omega t. And we're just going to plug in. We're going to plug in x at 2.5 seconds. And that's 0.2 times the cosine of pi over 2 times 2.5. So x at 2.5 seconds is approximately, we're going to go pi divided by 2 times 2.5. We're going to take the cosine of that answer, then times 2. Okay, and roughly it is about negative 0.14 meters, so about negative 14 centimeters at 2.5 seconds. Okay. Now the maximum kinetic energy is associated with the maximum velocity. So max kinetic energy would be 1/2 mv max squared. So 1/2 times your 10 kilograms times our Vmax. Remember our Vmax is 0.31. So 0.31 squared times 10 divided by 2. And so our maximum kinetic energy is about 0.48 joules. Now your maximum potential energy at amplitude, so this is at equilibrium. This is at amplitude. And according to law of conservation of energy, maximum potential energy, Umax, would be the same as the maximum kinetic energy at equilibrium. So in other words, would also be 0.48 joules. That doesn't change. Which means that is also the total energy. Total energy remains constant. Okay, now what we're going to do is we're going to graph the kinetic energy, potential energy, and total energy, not as a function of time, but as a function of displacement. That's a typo. Okay, now this in the middle is going to be x equals 0. And we're going to note that the amplitude on either side is about 20 centimeters. So we're going to go over, let's say, 0.01, 0.02, 0.03, 0.04, 0.05, 0.06, 0.07, 0.08, 0.09. This would be 0.1. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That would be 0.2. And you can do that in both directions. And we're going to make a dashed line that goes all the way up at that amplitude right there. Go all the way over 20 boxes to the left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's negative 0.1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's negative 0.2. And we're going to make a dashed line. Make a dashed line that goes all the way up that line right there. Okay, then you're going to make a valued line at a total energy of 0.48. So let's create our scale. We can go every 5 boxes up. So 0.1, this would be energy in joules. So energy in joules on the y-axis. This would be position in meters on the x-axis. So we can go 0.1, another 5 boxes up, 0.2 joules, another 5 boxes up, 0.3, another 5 boxes up, 0.4, and then 0.5. And you can see you're plotting 0.48, which is just a hair south of 0.5. So let's make a line. Okay, here's our total energy. Total energy as a function of position would be a horizontal line all the way across. Make a legend over to the side. Total energy, E, right, is going to be a black line. I'll make kinetic energy a blue line, and I'll make potential energy a gray line. So color code it or make dashed line systems, give some sort of legend or key off to the side. Okay, so we know that kinetic energy is going to be a maximum here at equilibrium, but it's going to be 0 here and here. So my blue curve is going to look like this. I'm going to make a blue dot right there at maximum energy at the equilibrium position. Now I'm going to make a blue dot here and here to represent 0 velocity and 0 kinetic energy. So that it's going to curve up like this and down, curve up like this and down to 0 right here. Okay, and then the gray curve is going to be exactly the opposite. I'm going to have maximum potential energy at the amplitude, 0 potential energy at the equilibrium, and it would look like a curve that is a vertical reflection of the blue curve. Okay, so that would be our position energy as a function of position. Okay, and so finally, we're going to graph position as a function of time. This one is a typo. This would be velocity as a function of time. And acceleration as a function of time. Okay, so my maximum position is 0.20. So I need to create a scale here. So I'm thinking I'll go, I don't know if I have 20 boxes. Let me see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, I don't have 20 boxes. So I'm going to go 1, 2, 3, 4, 5. That's 0.1. 1, 2, 3, 4, 5. That would be 0.2. So go down 10 boxes. 1, 2, 3, 4, 5. There's negative 0.1. 1, 2, 3, 4, 5. There's negative 0.2. Go ahead and make a dashed line across there to represent your constant amplitude that you'll be plotting in a moment. Okay, so I'm just getting my y-axis all squared away. My x-axis, well, remember guys, your period is going to repeat every 4 seconds. So what we can do is we can really spread this out. So say we only wanted to plot, let's say we only wanted to plot 1 cycle of this function. That's fine. Let's go every 10 boxes is 1 second. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 1 second. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 2 seconds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 3 seconds. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 4 seconds. Okay. And what I'll do is I'm just going to copy this exact same x-axis down on the other graphs because they're going to have the exact same scales. Go all the way down like there. 1, 2, 3, 6, and then finally down here, 1, 2, 3, 4, 5, 6. There we go. Perfect. Okay. Now, my first one is going to be x equals a cosine omega t. Remember what a cosine graph looks like. Cosine graph starts up here, looks like that. So how often is it going to repeat? It's going to repeat every 4 seconds. So that means at 2 seconds, it's going to get to the other side. So let me graph this in blue. My cosine graph would look like that. And there's my function for x is equal to 0.2 cosine pi over 2 times t. Okay, now my velocity as a function of time would look like velocity equals, I go from cosine to negative sine, so negative a omega sine omega t, where remember the a omega was your V max. What was our V max, everybody? Our V max was 0.31, okay, 0.31 meters per second. So our V is going to be negative 0.31 sine of pi over 2t. Now, remember, what does a negative sine graph look like? Negative sine graph starts in the middle and goes down instead of up. It's like that. It's going to repeat exactly as often. We need to come up with our x-axis scale. So I'm thinking you could probably use a very similar scale. We can go up 1, 2, 3, 4, 5. That would be 0.1. 1, 2, 3, 4, 5. That's 0.2. Nope, I can't make that scale work. Okay, so what I'm going to have to do is I'm going to have to go by, oh boy, let's see. We can go every 4 boxes, instead of every 5 boxes. So every 4 boxes would be 0.1. That should work. So every 4 boxes, 0.1, 0.2, and 0.3. Remember, we're making a sketch. We're not making it perfect. We're making a sketch. So every 4 boxes down, so negative 0.1, negative 0.2, and negative 0.3, where this is velocity in meters per second, time in seconds. The first graph was time in seconds, position in meters. Okay, how do I plot this graph here? Well, you're just going to start at 0. I'm going to start at 0. I'm going to repeat at 4 seconds, and it's going to come back through the graph at 2 seconds. I'm going to have this right here as my upper and lower amplitude. I'm going to be down here at 1 second. I'm going to be up here at 3 seconds. So my graph would look a lot like this. Okay, my velocity is a function of time. Okay, and then finally, my acceleration graph, I would go from a negative sine function to a negative cosine function. So negative a omega squared cosine omega t, where negative omega squared, if you remember back what we calculated our a max, there's our maximum acceleration, 0.49, pretty close to 0.50. And so that would be negative 0.49. That's our a omega squared cosine pi over 2t. That's our function that we're plotting. Okay, so thinking we can go, let me see, 0.1 1, 0.2, 0.3, 0.4, 0.5. And then same thing here. There's 0, negative 0.1, negative 0.2, negative 0.3, negative 0.4, and negative 0.5. Okay, I'm going to make a dashed line all the way across to keep our amplitude fairly constant. Remember, our maximum acceleration was 0.49, so I'm making it at around 0.50 just to acknowledge that. And our negative cosine function, we're plotting a negative cosine graph here, so that's going to look like starting at the negative amplitude, and it's going to go like this from the negative amplitude position. So I'm going to make a graph, a point at the negative amplitude. I'm going to make another point at 4 seconds because it repeats every 4 seconds. And at 2 seconds, I'm going to make a dot up here, which means my negative cosine acceleration graph is going to go up like this, back down like that. And those are my graphs of position, velocity, and acceleration, meters per second squared, versus time.